All right. So please interrupt me at any time during the lectures if you want to ask questions. I know it's very hard to interact with remotely like this, but let's try to make it a bit more interactive. So try to just interrupt me at any time if you have anything to say, any question, anything that isn't clear, anything you want to know, just interrupt me. Okay. So we live in very exciting times. As you know, there was a direct observation of gravitational wave in 2015. And that's a long history, starting from for the prediction of gravitational waves. It was just done at the birth of general relativity 100 years ago, roughly. These gravitational waves were already observed by indirect means with the Hulse and Taylor pulsar in 1974, where they observed a binary system. And because of the gravitational wave emission, this binary system is shrinking its radius. And you can see its decrease of radius with the time evolution. And you see it decreases according to the prediction of general relativity of the emission of gravitational wave due to the acceleration of quadrupole. So we will derive that in this class. Since the first direct detection, 2015, that you certainly know about, there's been also a notable detection of binary neutron star merger, 2017. That one was detected both through gravitational waves and through standard astronomy, electromagnetic radiation. So we now have three different ways to probe the cosmos. Directly from electromagnetic waves, so that's been done since ever, since humankind is watching the sky. We've been detecting particles coming from the cosmos. It was with hot air balloons at the beginning, when there was no when there was no accelerator. It was a very convenient way to do particle physics, to check all these particles coming and ionizing in the high atmosphere. And now we're waiting for neutrinos, also coming from different sources. But now we have a third way to probe the cosmos with gravitational waves, with direct detection. So it's kind of a revolution in the observations. And even though gravity has been a theory, has been really, pure theoretical developments for 100 years. Now there is this confrontation with experiment that is starting, and it's very interesting. So many black holes have been found. I don't remember the exact number, changing every week or 2 weeks, because there was one new observation every week or 2 weeks. You can see the list actually online. If you check on the LIGO-Virgo collaboration, you can check all the events, triggering events, if you want to. And you see there is a lot of activity. Some events are not are fake events at the end after analysis, but there are many triggers. So at the beginning of this month, well, of last month in September, there was the discovery of this black hole merger that leads to an intermediate mass ratio black hole. So here is the mass scale, and 100. So 160 solar masses black hole was formed. So there are also some neutron star here. You see, that's at this point two such observations, and one which is like the missing event, the neutron star with a black hole giving another black hole. So that one is unique for so far. So yeah, 2 people just joined. I was just explaining the overall picture of gravitational waves. You didn't miss anything yet. You can watch the beginning on the video that you will receive the link later on. Please interrupt me for any questions. Huh? So this main event, the first golden detection. So as a name, so GW is for gravitational waves, and the date is written in English American form, so 14th of September 2015. And there are two detectors for LIGO, one located in Hanford, the other one in Livingston. And these two detectors have detected the same signal. And here are after putting the templates of the gravitational waves, you can deduce the parameters of the binaries. And we will actually match this the template that we will construct in this class to this observation. And we will try to see if it fits well. So the first black hole has a mass around 36 times the mass of the sun. The second one, 29. And the final black hole mass is given by this. You see there is, if you add the two, you see there is a discrepancy of 3 solar masses. So the energy radiated is 3 solar masses, which is a huge amount of radiation. The spin is very high spin. It's so as you know, for the Kerr black hole, the spin is bounded by mass squared. So J is less than mass squared. So the ratio of J over m squared is called the spin parameter. So it's a number between -1 and 1. And here is around 70%. The luminosity distance is just the distance from the source. It's computed in megaparsec. And you can use a cosmological standard model to convert the luminosity distance to redshift. So that's the distance, okay. And you see that the event is only 0.2 seconds. So it's a very short event. Huh? So here is the network of current gravitational wave detectors. You have LIGO in the US. You have Virgo in Pisa in Italy. Geo 600 is for instrumental tests. It's not useful for detection, but it's useful for developing the technology. Kagra is the one in Japan. I will actually joining the network now. And Indigo will be the one in India. There are different types of detectors that will be coming as well. The pulsar timing arrays plan on detecting the very long wavelength gravitational waves on very large scales by detecting the timing of pulsars very far away from the Earth and trying to deduce very large wavelength perturbation. The LISA, which is the interferometer in space, will be launched in 2034 and will be operational in 2036. And it will detect different, also lower frequency bands than LIGO and Virgo, but much larger than pulsar timing arrays. And finally, the Einstein telescope is currently under active, active development. So there are tests already of the technology and of the geology for implanting it. So there are two possible sites, and one of them is actually in the EU region between Germany, Netherlands, and Belgium. And another possible site is in Sardinia. And the site will be decided in 1 or 2 years. So it's exciting that maybe there will be this Einstein telescope coming just at the corner here. So as for electromagnetic waves, you can describe the entire spectrum of gravitational waves. So here is our colors, you know, just for saying. So it's not really red and blue, but it's by analogy with electromagnetic spectrum. So you have the lower wavelengths here and the highest wavelengths here. So for the moment, we only detect this high range here with LIGO and Virgo. And you see LISA will detect lower wavelengths here. The pulsar timing arrays will be even lower. And then if you look at the fluctuations of the cosmic microwave background, so they talk about the very early phase of the universe. And if you can detect the spin 2, well, the tensor, what they call tensor modes in this microwave background, you will probe very the quantum fluctuation of the early universe in this range. So I'm not going to explain everything here, but you can see that there is a very rich spectrum with different types of sources and different types of detectors. It's like for electromagnetic waves, you have radio waves, UVs, and they all have a very different physics, and they require different types of detectors. So it's the same for gravitational waves. In this class, I will only focus on the physics relevant for LISA and LIGO, and especially the sources, which are the binary systems, binary black holes or binary compact objects. Now, since this is a class about theory and string theory, you might ask, well, what's the relationship between string theory and these gravitational waves? And I would say there is a big gap between the two, because there's a gap of energy between the Planck scale and this lower energy scale at which we are living and where we are doing observations. But there is a way to do effective field theory. So to consider that we are living with Einstein gravity and with some additional physics that might come from some infrared type or some low energy type physics, with whose origin comes from string theory. So the idea is to have general relativity plus suppressed modifications and get inspired from what string theory tells us what these modifications are. So in this spirit, there is this way to orbit organize the various modifications of general relativity that you can consider. So it starts from Lovelock's theorem, and Lovelock's theorem is very simple. So let's read the summary of Lovelock's theorem. It says that in 4 dimensions, 4 space-time dimensions, the only divergence-free symmetric rank 2 tensor constructed solely from the metric G mu nu and its derivatives up to second differential order and preserving diffeomorphism invariance is the Einstein tensor plus a cosmological term. So that's the uniqueness of Einstein's theory. So if you want to modify gravity, you have to remove some of the hypotheses. So you can remove higher order, go to higher order differential equations. You can remove the diffeomorphism invariance. You can go in higher dimensions, so you can add more fields. So you have a different type of theories that occur here. And very popular are the scalars because they arise naturally in string theory. In the first place, each time you do a compactification to 4 dimensions, inevitably you have scalars. Also, we want to explain dark matter, and one possibility instead of matter is to have additional fields. So you have various types of theories that have been considered, and the most famous one is scalar tensor theories. So I'm not going to discuss any of the theories, but some work has been done on gravitational waves production and propagation for these theories, but very little is known relatively to general relativity. Only for 4 or 5 classes of theories there are robust predictions, but even not for all stages of. So even for the binary black hole system, some is known for the inspiral phase, for the prediction of gravitational wave for the inspiral phase, but not for the merger, for example, where a nonlinear analysis is required. So very comparatively to general relativity, very little is known about all these modified theories. Already for general relativity, actually, the two-body problem is not totally solved. So here is a summary of the status of the two-body problem in general relativity that we would like to solve to be able to at least predict what general relativity tells us about the motion of two bodies. And in fact, there is a gap here. So let me explain this graph. You have on one axis the distance between the two bodies, so the radius between the two bodies. And on the other axis, you have the mass ratio. So M1 is a large mass, M2 is a small mass, and you have a mass ratio. When you have very long distances between the two bodies, then the space-time can be considered as nearly Minkowski. So you can do a post-Minkowskian approximation, and the motion is also very slow. So the velocities are small, and so you can do a small velocity expansion, so post-Newtonian expansion. In fact, because of Kepler's law, the two small parameters are related. I will describe that later as well in the class. So this post-Newtonian theory applies for very large distances of the bodies and has been very, very effective at describing the motion and the gravitational wave radiation in that regime. When you have a very large mass ratio, then the body of one of the massive objects is the Kerr black hole, and it's universal. This is one of the wonders of general relativity, that whatever the body is, how it was formed, or all its history, the final metric is the Kerr metric given by only two parameters. So if you have a very large black hole, it's given by the Kerr metric, and you have a small perturbation. So you can do perturbation theory around a Kerr black hole. And that's very effective for very high mass ratio. When you have comparable mass binaries, and when they're close to each other, you can study them with numerical relativity. So that has been done since the breakthrough of Franz Pretorius around 20 years ago, where he found a way to implement the numerical product GR using suitable gauges and controlling the numerical error. And the problem is that it cannot be pushed to high mass ratio because there are too many timescales. Timescales become too long, and it cannot be pushed too far as well, because then the timescales also are too long, and there is too much numerical error accumulating. So at this point, the largest numerical simulation can last around 6 months on supermassive computers, and it can do like a mass ratio of around 10, 50, but not more. So there's a gap here, which is called the intermediate mass ratio regime, and there are no very good waveforms at this point. So this is a challenge for the theorists working in this area to push the post-Newtonian theory to higher order, the perturbation theory to higher order, and push the numerical algorithm as well in their efficiency to try to cover that region. So these three methods can be also used to create a waveform model, which is an effective one, which is called the effective one-body theory, where, as in for Newtonian theory, you can reduce the two-body problem to a one-body problem. And then by using the information of the three perturbation theories or the three methods, you can arrive to some overall waveform that is interpolating between these different regimes. So I will stop a bit for questions, because I don't know if you have some. No, not especially. So here's the outline of the lectures. So we will discuss mainly the post-Newtonian, post-Minkowskian theory. I will start with a propagation interaction with test masses in linear GR theory. And then I will talk about the freely falling frame, TT and detector frames, and energy of gravitational waves. then the generation of gravitational waves, and we will go to the example of the quasi-circular inspiral of compact binaries. So that will be already enough for today and tomorrow. And if we have time, then on the Thursday, we will go to black hole perturbation theory. So I want to talk a bit about the Mathison-Papapetrou-Dixon theory, which is a theory for spinning particles, because we all know about geodesics and probe particles without spin. But there is an interesting theory when particles have spin, which has been a focus of recent attention in this black hole perturbation theory framework. And then if we have time, I will talk about the quasi-normal modes. So about the black hole spectroscopy, the ringing of black holes in the late phases of mergers. So for the references of this class, mainly is the book of Maggiore that I strongly recommend on gravitational waves. So there are 2 volumes. I will mostly use first volume and these sections, 1, 3, and 4. There is an excellent review also of Luc Blanchet on gravitational radiation and post-Newtonian theory. For the black hole perturbation theory, there's a good review of Barak and Pound. For the Mathison-Papapetrou-Dixon theory, Arthur has a very clear explanation as well. For the quasi-normal modes, classic reference is Berti, Cardoso, and Starinets. And I will also use my own lectures that I did 3 years ago in the Solvay lectures. All right, let's start with the basics. Propagation. Propagation in general relativity. So what is the theory of general relativity? It's a theory described by an action given by the Einstein Lagrangian, also the curvature, and the matter with the prescription that the coupling is minimal. So one takes the Lagrangian of the standard model or any matter coupling that you have, and replaces the metric with the Minkowski metric with the curved metric, and each derivative with the covariant derivative. So that's the recipe for building general relativity. So the strategy tensor is given by the variational derivative of the matter with respect to the metric times 2 over square root of g. I will try to keep the C factors as well in this lecture. So Einstein's equations, as you know, given here. And the theory is invariant under diffeomorphisms. A general diffeomorphism changes the coordinates x into x prime. And under this coordinate change, the metric transforms as a tensor, 2 times covariant tensor, where the primes go in this way, as you know. So now let's start with perturbation theory. So we imagine there is a coordinate system in which the metric is numerically given by the Minkowski metric in Cartesian coordinates plus very small numbers. So h is numerically smaller than 1, it's a small number. Then the residual gauge transformations that apply here in this theory, such that h remains small, well, we can take any psi whose derivatives are less than 1. Indeed, the linearized metric transforms in this fashion. So as you know, you transform it using the Lie derivative, but the Lie derivative of Minkowski gives you just this term. So the derivatives of psi symmetrized. So this is the linearized perturbation of this is the diffeomorphism of the linearized theory. It's given by these transformations. So in particular, there are 2 particular transformations that leave the linearized metric invariant And these are the symmetries of linearized theory. If you take a translation parameterized by a constant b, or if you take a Lorentz transformation parameterized by an anti-symmetric byte tensor times the coordinates x, this term is 0, so the linear metric is invariant. So linear metric is invariant under Poincare transformations.
Sorry, the H mu nu is from the minimal coupling, right?
So the H mu nu is the part of the metric. So it's not the minimal coupling. Because the minimal coupling is all the matter. So it couples the matter fields. So SM is a function of, for example, electromagnetism, the A mu,
okay,
or various other fields, and you change, you write down your matter in Minkowski spacetime, and then you make that substitution. But now all this theory depends on the metric, so which appears everywhere, both in the Einstein term and both in the matter term. And now we just expand the metric. So H is the linear perturbation of the metric around Minkowski now.
okay.
So now if you expand the Riemann tensor in terms of this linear perturbation, you will find this. So we're going to prove it in a minute. And then it's natural to define two quantities. So the trace of H, which I call H, which is the contraction of the background Minkowski metric with H, and the trace reverse perturbation. So it's H minus this quantity, and it's called H bar. And it's called trace reverse perturbation because when you compute the trace of H bar, like this, you get an H from this term, minus, so eta, the trace of eta is 4 divided by 2, so it's 2 times H, so it's minus H. So this is why it's called trace reverse perturbation. And note that you can invert this by substituting H equals minus H bar. You can just put it on the right-hand side. And so you get this equation. So now let's just prove that this Riemann is given by this. So let's do a little exercise so that you don't well, so that you participate a bit more. So I will try to break this room so that you can discuss to each other. So let's do a breaking up of 2 or 3 participants per room. And if you can work out this linearized Riemann tensor, and up here we go. So now you are in broken rooms. Don't hesitate to say hello to each other, spend some time to socialize. It's also part of the objective of the Solvay school, is that you get to know each other. So you are, each of you is with 1 or 2 people, and see if you can derive this equation. I'll give you a couple of minutes. So do you have it at this point, or you need more time? I'm not sure. It's hard to notice if you are not to do this online. Wait just a couple of minutes. All right, so let's correct just this. So I'm not sure, yeah, not sure if you're done or not. I will close the rooms now. It's very hard not to get feedback, to know exactly what's going on without any feedback. So the breakout room will close in 1 minute. So here is the solution for you. So could you see the screen? Could you see me writing? Can someone tell me if you see me writing?
No.
No. Okay.
Sorry, I got a problem. My computer crashed.
Okay. So do you see the screen now? Yes.
Yes.
You should see the screen now. Okay. So right. So oops. Very hard to manipulate this. So the gamma has two terms. So there's basically G and then a BG with two terms. So once you replace G by eta plus H, the derivative of eta is 0. So if you want the linear term, you need to put the H inside of the G here and the eta here. Otherwise, you don't get a linear term, right? So the answer for the variation of a gamma is just this one. So plus the minus is always with a, oh yeah, put a beta here. I shouldn't put a beta. We already are using it. So we use a delta here and here beta gamma. Then for the Riemann, so we have terms like this. Now we are looking at the linearized case, and all the gammas in Cartesian coordinates are 0 when we evaluate at eta. So all these terms are 0 at linear level. So at linear level, we will only have.
Oh, smarter.
What's happening? So we have these kind of terms only. All right. So it's the gamma variation of beta minus gamma exchange with delta. So we need to write this down. So I have to be a bit careful with the indices here, especially I use already a delta here. So we put an epsilon. So let's try to be careful with the indices. So I have a derivative with gamma in front because of this one. And then inside here, so the epsilon is a special index, so it comes here. And I'm left with the beta and gamma, which have to appear in the remaining indices. And so is that one minus when I change gamma with delta. So gamma, so these two are changed. So the gamma and delta are changed. Huh? All right, and now here you see, because of this minus sign, this term and these terms are, you can commute the derivatives, so they cancel. And so you are left with 4 terms. And these are the 4 terms that are written in the first line here of Teams of the presentation.
Sorry, Geoffrey.
Yes.
So for the gamma squared terms, you write gamma evaluated at the background is 0, but do you mean that because it is squared, it's of higher order, or the gamma is 0 itself?
Yeah, so we are looking at linear order now.
Yes.
So this term will appear at order h squared.
Yes.
And now we look at the linear terms. Indeed. So
sorry, I have a question on the notation. When you write the delta in front of the gamma, so delta gamma and also delta r alpha beta gamma delta, you mean the linear term that comes from okay,
so that's the that's the linear variation. Yeah.
Okay, thanks.
Yeah. So yeah, delta gamma is the linear variation. All right. So we are back here. So we just derived this one. Let's continue. So now we have this linear Einstein perturbation. So given by this term equals to the stress energy tensor. And you see that it's very complicated. So we want to use the gauge freedom now to simplify the problem. So we want to go to a harmonic gauge, which is also called the Donder gauge or Lorentz gauge. So all the same. And it's given by this. So we want to fix this condition. Now let's prove that you can reach it using a gauge transformation. So if I do a gauge transformation in linear theory, we see that's given by changing h with these 2 terms. But here the trace reverse perturbation will be, we will change also its trace because of the definition of the trace reverse perturbation. Right, that was written here. So we do a -1/2 and then we transform the trace as well. Right. So the trace is 2 times the divergence of psi, and with a factor of 1/2, the 2 cancel. So we get this transformation law for h bar. So the derivative transforms like this derivative, and then minus. So you see that here this term and that term will cancel because of the divergence here commutes with d mu, and that term will become a d mu. So these 2 terms will just cancel here, and we get just a box here. We get a D'Alembert times psi. So if originally we have a divergence, which is non-trivial, then we need to solve this equation to reach harmonic gauge. And this is always possible because there is a green function for the D'Alembertian in flat space. We can inverse that. And actually, it's not even unique. We have residual gauge freedom. And the residual gauge freedom will be the harmonic functions. So any vector with D'Alembertian is 0. So this is the harmonic gauge. So now let's imagine we are in harmonic gauge. So you see here, this is now becoming 0. This is 0. This is 0 because of this row here, this row here, this row, and well, W0. So we have this equation. Note that if you act with d nu, you can commute the d nu here with the derivation, and you find the stress tensor is conserved by consistency, which is a consistency condition. So this equation is important both for generation of gravitational waves and for propagation. Now let's look at the propagation. So outside of sources. So this stress tensor is 0. We have an equation like this one, and that means that the gravitational waves propagate at light speed, right? Because it's a wave equation that with the velocity equals to the speed of light. Now, I mentioned that we have a residual gauge transformation, which is parameterized by all the vectors that are harmonic. Then, actually, if you have an harmonic vector, you can build psi, this psi, which is given by this. And this one is harmonic as well. I should have done an exercise on this, but you can prove that this one is harmonic. Since this psi is harmonic, you can use these four such fields to remove components of h mu nu bar. So we already removed 4 components using the harmonic condition, and we can remove 4 components using the residual gauge transformations as well. So we will be left with only 2 propagating degrees of freedom in h bar. So it's always the rule when you have gauge invariance is that you kill the degrees of freedom twice. You kill it once by gauge fixing, and you kill it the second time because of constraints. So it's really 10 minus 2 times 4, and you have 2 degrees of freedom. So to see now where are these 2 degrees of freedom and to isolate them, we'll use the residual gauge transformation. So let's choose psi 0 to fix h bar to be 0. So we can do that because of the following reason. So if you take h bar plus one of these psi, so you add this perturbation, which is harmonic. I didn't prove it, but it's an exercise for you at home to prove this is harmonic. So trace this tensor now. So you get h bar on this side, and here the trace of psi is what? Well, you have two times the divergence here, minus 4 times the divergence. So if you want to fix this to be 0, you want to solve this equation. And this equation, you see that you can always solve it by integrating over time. So you solve for the time dependence psi 0, and you are just left with some residual constant of integration of this time integration, which are given by psi 0 function of space only, which are harmonic. So these are the residual gauge transformation after you fix the trace to be 0. Once you have that, then the trace is 0, so h bar is h in this gauge. And we want to fix, moreover, that h0i is 0. And we can do that because, again, if we consider a harmonic psi, we can build this psi mu nu. And then we want to look at this sum, and we want this sum to be 0. So let's compute what is psi 0i. So you have these 2 terms, 0i and i0. And this one is 0 because there's no mixed component in the metric of Minkowski. So you want to fix this to be 0. So we reorganize the term. We put the d0 here, and this one's on the right-hand side, and you can integrate that over time. So you can solve for the xi, and you are left with a constant of integration because you can add any constant which does not depend on time, and it still solves this equation. So this is the residual gauge transformation. So now we have h0i also to be 0. So together, the trace B0 and H0i to be 0 is called the TT gauge. And it still has some residual gauge transformation that are left, but less than before. And this TT gauge can be reached only once without sources, because you need to use harmonic functions. And remember that the H bar is not harmonic if you have a stress energy tensor. H bar has harmonic only outside of sources. So you can reach TT gauge outside of sources. Right, so now let's look again at the divergent condition to see what it implies, because we are already in transverse gauge for H. So we imposed that already earlier. But what does it imply? Now, if I look at the mu component of this transverse condition, I sum over 0 here and over I here, and with a 0 component here. So we already fixed H0I to be 0. So it means that H00 does not depend on time. It's a fixed potential. So there's no propagating mode because there's no time dependence. And this one is a Newtonian potential. So for propagation, we ignore it. It's a linear theory, so each field is independent of each other in linear theory. We just ignore that one. For mu equals I, we have to sum all the components. The 0 again is 0 because Hi is 0 is 0. We only have a special component. So at the end, we have found that in this gauge, we have these conditions. So I mentioned that it can be reached inside of sources already. Now, to solve these conditions, where we do a Fourier transformation, so we write this TT gauge perturbation as some Fourier components. So with k modes in spatial direction and omega in time, and with a polarization vector by tensor EI, which is a function of k. So because of the propagation speed, because it's harmonic, omega has to be related to k, to the norm of k with the speed of gravitational waves, c. And this k mu vector is the time component, omega over c, and k as a special component. It's convenient for later to define the direction of k, which is with a hat to mention that's the unit vector, which is k, the vector k divided by its norm. If we look at, for example, along the n-axis, this n, well, it's transverse here. So if I apply di, you know, it will be transverse to the direction of propagation. So there will be no z component. And then we have something traceless. So if I have a h plus here, I need to have a minus h plus because so that its trace is 0. And it's of course symmetric because it's the metric. So if I have a h times here, I have a h times here. So and here is some exponential. I take a real basis, so I take a cosine. So here is the linearized propagation of linearized gravitational wave propagating along the z-axis. There are two polarization modes, which are called h plus and h times. So if I look at the metric, so I have the Minkowski metric plus this linear perturbation. And you see that this linear perturbation appears so in the xx squared term here. There is a mixed term in the xy here. And there is a minus in the y square term. So here is the linear metric containing a planar gravitational wave propagating in the z direction. Is that clear? Okay. So a convenient tool, it's called a TT projector, because the manipulation we did here it requires to solve differential equations to reach this gauge. And it's a bit complicated to do all these to solve these differential equations here. You don't want to do that every time you look at a gravitational wave. So a better tool is this projection. So once you have a plane wave, which is in transverse gauge, which is this harmonic, harmonic gauge, but not yet in TT gauge, you can reach the TT gauge by acting with this projector. So this projector is built in this way using n as a propagation, where ni is the set of vectors, unit vectors on the two sphere. So let's prove this. Let's try to prove all this. So here is the projector, and let's try to prove it's a projector. You obey this condition. That is transverse, traceless, and if we start with a harmonic transverse perturbation, that it will remain harmonic and transverse. Otherwise, it will just break what we built. So it has to be true as well. So let me try again to break the room, and see if you can do exercises. Yes.
Sorry, the problem is that when you put us in the rooms, we don't see the slides, so we cannot.
Ah, oh, you don't see the slide anymore.
At least I didn't. I don't know.
Okay, let me try again, and maybe because I clicked on I was clicking on the breaking room to see what was happening, and I think that prevented the slide sharing. And I don't know, in practice, you can actually work together like this. I don't know if that's a system where you can actually. So basically, the idea is that you take a sheet of paper and try to write and try to discuss and try to do it together. Let me try again, and if does it work. So I open the rooms. Okay, and now do you still see the screen?
I think the problem is that when we leave to the breakout rooms, we can't hear what you're saying in the main.
Ah, you cannot hear me in the.
Yeah. Because now I haven't left yet. If I go, I can't hear you anymore.
Well.
For example, me this time I have a problem. I don't know how to leave, and last time I tried, my computer crashed. So.
Well, maybe we will not do this breaking room then. Oh, and you know, these breaking rooms will stop in 1 second. Okay. Well, let's not do the breaking rooms. If there is technical problems, then the idea is that the breaking rooms will allow everybody to be discussed with others. Then just try to do the exercise. Okay, so breaking rooms are cancelled because of technical problems. So just try to do the exercise by yourself then. I put some hints already. So some intermediate steps which are useful. So try to get these intermediate steps. So who would like to have a correction, or who would like to have more time? I cannot do a poll, actually, because if I do the poll, I stop the screen sharing. So at least maybe some people can react if you prefer to have a correction now, or if you prefer to wait longer.
Maybe a bit longer, if that's
Yeah.
okay.
Yes, I agree.
Yeah, sure. It's a longer. It's pretty long actually to prove everything. But keep trying.
Hi, can I ask a question?
Sure.
This gamma AB that you defined on the hints.
Yeah, the metric on the sphere.
Okay, that's
theta is theta and phi, and gamma AB is the metric on the sphere. Actually, that one is not strictly needed for the argument, but it's a useful thing to know.
Thanks.
So I think we should keep moving. So I'll do the correction here on the tablet. So do you see the tablet?
Yes.
Yes.
Yes, okay. So let's first prove that P is a projector. I want to see something like this. So if I plug in a delta and P, delta jk minus nj and k. So this one is a delta. So with this term, then with this one, I have plus ni and k. With this one, minus ni and k. And with that one, I have a plus ni and k, and then n squared, which is 1. And these two cancel. So this is this pik. So P itself is a projector. Then it's possible to just square this. So for the I don't think it's necessary that I do it explicitly. It's a question of plugging in explicitly now in terms of P, and then doing squaring it and using this property. So it's pretty straightforward. Now for the two, so we want to prove that ni KL equals 0. So for that, it's useful to first start with computing ni pi k, which is delta minus ni and k. So this one is nk minus n squared nk. N squared is 1, so this is 0. So pik is transverse. So then it's easy because this one contains only p's. So there is always a p that is killed, that is summed here, so it's 0. And same with the k. Yeah? It contains only p's, and the k is summed, so the k will just just by using that this is 0, it will just kill it. So for the trace, I want to prove this trace is 0. So it's useful to first compute pii, which is delta ii minus ni ni. Ni is 1. Delta, careful, is 3 because there were 3 space-time dimensions. So pii is 2. So now we compute explicitly lambda. So you don't see my screen, so let me put again the definition. So lambda ikl is pik pjl minus 1/2 pij pkl. So if I do the trace, I have a pil. I should write it. So this one is pil minus pii pkl. So the first one, we use the fact it's a projector, that's a pkl, and this one is a 2 divided by 2 pkl, so 0. Same for the other trace, huh? The other ijkk is just the same proof. All right. Now for the harmonic and transverse condition, that's more tricky. So let's look at the transverse condition. So we already know that this is true. And we want to prove that dj of ijkl hkl equals 0. So we want to prove this. So note that here, once we have a trace, the trace is killed by the lambda. So you can rewrite this condition with an h or h bar, it doesn't matter. So if you want, you can put a h bar here. So you want to prove either of the two. Let's use this one because we already know that the decay of h bar, this one is divergence free. So it's more natural to use this one. So now the derivative can act on each of them. So let's first let's write dj on the first, and then we have the other one. So for the first one, we use the fact that this j derivative, I can put the index up or lower with the delta. It's just a metric, a Euclidean metric, so I can put it up or lower. So it's really a radial derivative times nj plus an angular derivative with respect to the angles with the Jacobian, which is given by this one. The derivative with respect to the coordinates, Cartesian coordinates with respect to, and this theta is really the two angles. So now NA and I as a 0 radial derivative, it only depends on the angles. So this one is non-zero. So the R of lambda ijkl is 0. It does not depend on radius at all. So I can, I'm allowed to just look, this dj is really this one, lambda ijkl h bar kl. And the other term has to be treated separately. So here now, the point is that when you here we only act on ni that are inside of this delta. So we have to use this property that this one is actually a pij. And how do you prove that one? Well, that's somehow that's by definition, because the this one is a projector onto the spherical coordinates. This is what this is doing as well between this product. Okay, how do you prove this?
Sorry, you can also do it directly by writing Ni as xi over r. And just act with dj. So we want
here,
dj of Ni, right?
Yes. You mean yeah? We can dj. You can just say dj of Ni is directly given by Pij. Yeah. Yeah. So Ni is xi divided by r.
I guess there is a 1 over r.
Yeah, you mean you have here r di. This is what you're saying. R dij. This one is So yeah, I want us to compute that one. Now, yeah, so to see that here, yeah, it's a bit tricky, huh? So the overall factor of r, we were looking for something equals 0, so it doesn't matter. I was ignoring that. You're right. So now yeah, we need to compute this one. Huh? So let's just compute it. So this one is p I k p j l minus 1/2 p I k p j. So this one. So now I want to use this property. So what is I need to know what is this one. So in this one, there is a delta ik minus ni and k. So it's minus acting on the first, minus acting on the second. So it's minus pij and k minus ni pjk. So one has to use these properties here. It's a bit longer. So so that's the first term, pjl. Then there is the other one with the divergence of pjl. So this I becomes a j, so I have a minus pjj nk minus nj gk. And then there's minus 1/2, again, the divergence with the I index 3. If I didn't do a mistake. And then there is another term on the pkl now. All right, hope didn't do a mistake. So now this n contracted with the p is 0. This p, summation of p, we said it was 2. And now with these contractions of indices, so let's rewrite it. So I'm here. So once we have a projector, we can also contract it. So P, I, L, and K, because this projector and that projector contract nicely. Minus Ni, P, K, L. Okay, with these two contract nicely. Here I have a minus 2 times nkpk. Oh, but that's 0 because the n contract with the p is 0. So what do I have here? Plus 2 over 2 nipkl. And then I have a plus 1/2 this p, and p contract nicely as well. Um, 1/2 p, l, j, and k. That's it. So this term cancels that term. And I have put a j index 3 here, which does not make any sense. Here it was a j index. Yeah, the j index was contracted now. Here the I index is not contracted. The j index is contracted. So here the free index is the I. Yeah? It's I here. Otherwise, it doesn't make sense. So overall, seems that I didn't get it right. So I have this term which left, and that one I have a minus, so it's minus 1/2 p I l and k. So I got this term. Well, I should have gotten 0. Yeah, it's contracted with something symmetric. So H, this is, I computed, yeah, dj lambda ij L, and now I have to contract with H key KL, and that one is symmetric in K and L. So these two terms cancel, and I get 0. Okay, good. Okay, well, it's a bit long. There's a similar thing to be done here, the other term, not there yet. And for the other part, box KL HKL to compute this one. So box is so it's two derivatives contracted n. So that there are 3 types of terms. There's the box acting on lambda. There's the term mixed with a factor of 2 because there are 2 of them. And then there is the box acting on H. So we want to prove that this is 0. This one is automatically 0 from the assumption that we have already something harmonic. This one can be computed. And for one first has to know that box of pi, one first has to compute that one, etc. And this one requires more care as well. And we have to use that the derivative of H is trace. So here again, it's better to put a H bar to start because the traces are killed anyway. So we start with something which is divergence free. Okay, so it's a bit long, too long to do it all here. At least I was able to get this one right. But do you want me to continue, or is it more or less clear how to get there?
It's okay, I think.
Yeah, it's clear.
Okay. Yeah, it's clear. Like, the strategy is there is just a lot of computations to do. Okay, let's try to move forward.
Hey, just one question.
Yes.
So why does Pij equal to partial INJ?
Why Pij equals to partial. So Pij is a projector into the directions orthogonal to the normal. So you have Cartesian coordinates, and normal is pointing outwards on the sphere. So the projector is a projector onto the sphere. So this PIJ is really a projector orthogonal to the normal, which is the outward pointing normal. So it's a projection onto the spherical direction. Does that answer the question?
Okay, thank you.
Okay, let me finish this section and then we will take the break. Well, actually, that's at the end of the section. Well, so maybe it's best that we take the break now, and then I will continue in 15 minutes on the test masses. So if you want to ask me questions during the break, feel free to.
Hi, maybe a practical question. Will you send us these slides after the lecture at some point?
Yes.
Yeah.
Yes, I will send you all the slides, and you will receive also the video recording.
Perfect. Thank you.
Geoffrey?
Yes.
In previous slide, you mentioned plane waves, but I don't see if you have ever used the Hij to be a plane wave. I mean, I think this TT projector can be defined for any. Maybe next slide. No. Yes, here.
Oh, here.
Yes, you're given a plane wave.
Here,
I mean, it can be any
here
wave, right?
Oh yeah, here it can be any wave. Yes.
Yeah.
Yes. So this one is a plane wave because
Yes.
it's just an overall cosine, and it's the simplest one to look at. But now you can, it's an inner series, so you can do a combination of such plane waves. So with combination of plane wave, you can do any types of wave you want.
Yeah. And the
Just
TT projector, for example, I think can take spherical coordinates, and then at each point on the sphere, the n is the normal to the sphere at that point, and then the projector projects onto the plane tangent to the sphere, right?
Yes.
Mm-hmm. I'm sorry, I have another question about the introduction. So you mentioned this Hofstadter pulsar. So I imagine then that this system also emits electromagnetic radiation and other types of, I mean, energy loss.
Yes. So these detections actually are electromagnetic observations.
No, I mean, no, the second slide, I guess. You show this, yes, this plot.
With this one maybe.
No, the plot for the Hofstadter pulsar. The energy, yes, this one. So
yeah, that was electromagnetic observation.
Right, but when you say that this change in the energy, so when you say that this matches with the prediction of GR, I mean the system also emits the electromagnetic radiations, and so I mean, even if there is no gravitational wave, the orbit should shrink maybe slowly, right?
That's right. Yes, I think it's negligible. I think it's totally negligible.
compared to the gravitational wave part.
Right. I cannot tell you how many orders of magnitudes, but I would say it's several orders of magnitudes suppressed.
Okay.
Yeah. Here, really, the gravitational wave radiation is a big fraction of the rest mass energy, which is the highest, energy reservoir of this system. This, compared to nuclear reactions inside of the stars, there is some fraction of the rest mass energy that also goes into radiation, but it's very small compared to. I mean, here for the merger here is dramatic, and because this is really at the end of the merger where you get most of the radiation coming out, but you can see already that it's a significant fraction of the mass that is radiated.
Right. Yes.